So we come to part 2 discussion of nuclear magnetic resonance. I hope like you are thorough with the core principle of NMR in the part 1 video. So in this session we will be seeing two aspects of NMR. One is instrumentation and experimental strategy of NMR technique. The other aspect is applications of NMR. Coming to instrumentation and experimental strategy, NMR works in three stages. One is magnetization, second relaxation, third one spectral data reading and its decoding. So with which you will be coming to know about information related to physical, chemical as well as structural properties of a given molecule. And this is being done using an instrumentation setup where it has three basic parts. One is your sample chamber, where you will be keeping the sample either in solid or liquid state. So in case if you are keeping the sample in solid state, that's what we call solid state NMR. If it is liquid in nature, that's what we call liquid state NMR. And this sample is subjected to magnetic pulse induction or stimulation through magnetic placed vertically to the magnetic sample chamber. And the third part of NMR by instrumentation includes detectors, which detects energy released from the excited sample by a magnetic field, and this is being detected by a coil placed around the sample chamber. And these coils tend to receive the signal either in the form of electromagnetic radiational frequency or thermal frequency. In case of nuclear magnetic resonance, in most of the cases it will be reading that electromagnetic resonance frequency, and this detector converts it into an electric signal, and this electric signal will be converted into a spectral peak depending on the electron energy potential. Okay, fine. So based on the nature of atom and its electron intensity, the peak range will vary. For example, this may correspond to carbon, this may correspond to hydrogen, this may again correspond to, or this may correspond to nitrogen. So what does it mean? So you are getting a peak in this following order. That means like your molecule is having CHN. So this for your practical understanding, it's a bit more complicated than what you see in the board. Okay, and this is a general instrumentation of nuclear magnetic resonance. And how this is being executed? It is being done in three stages. As I told you, first stage, magnetization, where you are subjecting the sample to magnetic stimulation, which is being done in three ways. First one, continuous wave nuclear frequency. So this is a conventional traditional method where you are continuously eliciting the atom of a given molecule in a consistent magnetic condition. So it's like now you are playing with the magnet. What you do, you just taking the magnet here to the ion rod. Then what you do, you will be just trying to play with it. You do not try to attach the ion with your magnet, or in the same way you do not take the magnetic near to the ion object. So what you do, you will be keeping it in a particular distance, and you will be keep on playing with it based on the attraction and repulsion. So in the same way, you are subjecting the sample in a continuous way with a static nuclear magnetic elicitation, and that's what we call continuous wave nuclear frequency. The second thing, methodology, pulse field nuclear frequency magnetization. From the word itself you can say, so you are going to give a short pulse of magnetic excitation. So here what you do, the first one, you are keep on activating the atom, and you are trying to read the changes in the form of spectral field. The second one, you are just giving it for some time duration, for example 5 seconds or 10 seconds. Then what you do, you allow the molecule to come to the original level. Then you try to see what kind of spectral peaks you are obtaining. Spectral peaks என்ன சொல்றேன்னா, so once the atom is elicited, it is going to the energy, high energy level. Then when it comes to the ground level, it releases the energy. So that's what you will be reading in NMR spectra. If you are giving it in a short pulsed field, then you are allowing the molecule to rest for a while to come back to its normal stage. So the excess energy will be released out, and that will be read as nuclear frequency. In the third one, Fourier transform. This is actually a development of pulsed field in nuclear frequency. So here what you do, you will be focusing on electron shells of each and every atom. So these electron shells, depending on the location, they tend to respond to external magnetic stimuli in different way. So this is the concept behind Fourier transform. So like it's basically you are going to study electron density of an atom and you are correlating with the spectral peak. So this is what it means. So using these three strategies, what you do, you would be studying, or you would be magnetizing the sample, and once this is being done, so the excited atom shall release the energy, as you know very well, which is being read by detector, and this is done in this process or in the stage called relaxation stage. So relaxation stage, what you do, you allow the molecule, okay, you allow the molecule to go to that excited stage. Okay, for example, this is a normal atom. Okay, so normal atom A not much. So this is the excited atom. So the same atom in its excited condition, it has become bit more enlarged because of the excited electron movement. The same way proton also expanded. So what happened in the relaxation stage, you allow this atom to come back to the normal level. Okay, so during this process, excess energy, whatever being absorbed, that is being released, and that you study in the form of, that you receive it in the form of electric signal, and it is constructed as NMR spectra in third stage called spectral data reading or spectral data construction. So this is a methodology of NMR. So since I have discussed most of the information related to spectral graph, spectral data in the core principle, I have skipped most of the things in this discussion. So coming to an important strategy related to NMR spectra data analysis, I want you to understand two strategies. So one is nuclear coupling and decoupling, and another one nuclear overhauser effect. Okay, nuclear coupling and decoupling. So this is a technique to study your NMR spectra, where you will be studying the information from the NMR spectra using your theoretical knowledge. How do you do? So I'll put a NMR spectrograph, and I've told you very simply that this P corresponds to carbon, and this is corresponds to hydrogen, and this corresponds to nitrogen, but you won't get a spectral graph like this. Okay, obviously most of the NMR spectra, you'll be getting overlapping peaks, what you are seeing in the board. So what you do, so this one single peak, you are getting 3 different ranges. That means there are overlapping information received by detector from the magnetized sample. Okay, so what does that mean exactly? You have to separately read each and every peak, and you need to find out, so which one comes in the first, which one comes in the second, and which one comes in the third. Okay, so that you need to do with your existing theoretical knowledge. So that is being done with this concept called nuclear coupling and decoupling. Okay, so in this one, what they do in general, so based on the wavelength and energy, that in electron intensity, so you will be separating the peak values first. Then you will try to find out what kind of atom would have produced this effect. Okay, so this is what we will be studying, and this is information, separated information, okay, is again being studied, and the order will be deciphered. Then you will be integrating once again. So this cyclic decoupling and coupling is what we call nuclear coupling and decoupling in decoding the NMR spectral information. Fine. So coming to the next one, nuclear Overhauser effect. So this effect is being generally used to study the three-dimensional structure of biological macromolecules. So what exactly happens in this strategy? So for example, just take a protein. So protein, you know very well. So it is made up of amino acids, isn't it? And each and every amino acid has its own structure. One central carbon surrounded by hydrogen, uh, carboxyl group, amino group, and there is a side chain, isn't it? And side chain, they tend to have their own branch. So each and every atom in the side chain produces one effect. In the same way, central carbon and your amino group, carboxyl group. Okay, so in nuclear Overhauser effect, what you do, you will be studying each and every atom separately in an amino acid first. And then what you do, so in most of the cases, all the amino acid atoms are placed together. So what you do first, you would be comparing the information of each and every atom, then you will be constructing one amino acid structure. The same way, you will be studying each and every amino acid individually based on its nuclear Overhauser effect. What is nuclear Overhauser? Now from the word itself you can say Overhauser. Okay, there's overlapping information between the spectral graph, and based on the information you are integrating the data. For example, if I am taking a subject studied by yourself, all of yourself, I can easily predict that you are studying MSc Biotechnology. If I study some other student community in microbiology department, based on the subject composition, I can predict the major core subject of the students. They may be studying MS in community, I can predict. So this is how what you do. You will be studying the spectral peak and you will be trying to find out each and every atom. Then when you are fitting it, you will come to a conclusion. So if you are getting a spectral graph like this, it would denote amino acid. Okay, based on the nature of spectral graph, then you will find out what kind of amino acid it means. So likewise, you will be fitting atoms information one on one, then you try to find out the major molecular nature of that particular atomic composition. So that's why you will be decoding the information about each and every amino acid. Then based on the intensity of the spectra, you can find out whether your amino acid is located on the surface of the protein or interior of the protein. So interior of the protein will produce a smaller effect when you compare with the surface of the protein. So based on this, you can locate the topology of atoms and molecules in your protein molecule. So this is what you do. You'll be trying to find out the three-dimensional structure of protein. This is what we call nuclear Overhauser effect. So all these informations are there in the study material shared by me. You can find some 9-page NMR short notes where you'll be getting the same information. Coming to the next aspect, applications of NMR. NMR is being applied in three major ways. First one, molecular characterization. That is what we have seen so far. If I am giving a chemical molecule or biological macromolecule, you can study the atom level information about the molecule and you can predict what kind of molecule it is and what is the physical, chemical and structural aspects of it. Next one, just now told you, 3D structure, three-dimensional structure of biological macromolecules can be constructed, especially protein and protein-related macromolecular complexes. One major drawback behind this technique is due to the technical constraint, only low molecular weight protein structures can be studied, maximum 20 kDa to 20 kDa, that's a maximum limit. And third one, molecular fingerprinting. So each and every atom has its own NMR spectra. In the same way, each and every molecule and macromolecule, they have one spectral graph reading. So if I'm giving a spectral graph reading, you can easily predict what kind of molecule it is. So basically, it helps you to track down the molecules present in the given sample. So this is what we call molecular fingerprinting. This is also being done using NMR spectra. Okay, with this I hope that you are clear with the NMR technique. So for detailed information, just refer my study material. So in case if you have any doubt, just call me or text me. Even if you want to share your opinion about this video lecture, just put it in the comment section. Thank you everyone. Thank you.